For the 2012 Flight B summer exam, it requires a couple of steps in order to get the final answer. The first step is to convert the rigid body equations of motion, so these two here, which are for a phugoid, into state space form. The second part is, once you have it into state space form, you have to apply the determinant rule in order to get the characteristic equation. So the characteristic equation will contain the eigenvalues, or the roots of the polynomial, and the idea is that you're going to expect them to be complex and stable in order to be able to get a damping ratio value, and to also calculate the undamped natural frequency. So for the first part, so you have it normally in this compact form: d on dt minus xu delta u plus gravity times change in pitch rate equaling 0. So xu is change in forward force over the change in speed, and the second equation is zu delta u, and then you've got the reference speed and the rate of change of pitch rate. So it's represented in this compact form, but the first step you have to do is convert it across. So the d on dt, say delta u, and to get it across into state space you have to represent it in terms of, it's the same as delta u dot. So if you apply that to the first two equations, you end up with, so u dot minus xu delta u plus gravity delta theta is equal to 0. The second line becomes negative zu delta u minus u naught delta theta. So once you have it in this form, rearrange it to get the rate values on the left hand side. So for the first line, it's delta u dot is equal to xu delta u minus g delta theta, and for the second line you've got delta theta, but you still have that reference speed value there, which you'll have to cancel out in a second. Now, even though there's no delta theta value here, I'm just going to write it out anyway, because that's how you'll end up making the matrix. So delta theta dot, to get rid of the reference speed value, you can divide both sides by u naught, so that'll cancel out here, but then you'll end up with a u naught on both sides. So the form that you normally are after is x dot is equal to ax, so this is your states, this is your rates for the states. So in order to get this into that form, you're just left with, which is already in that form. In order to form your matrix, you can look through, and because we've already got it into this form, you know that xu delta u and negative gravity delta theta is going to give you delta u dot, so the disturbance in rate of change of speed. But the same thing with the second line, and because we had a 0 here, that 0 just translates straight across. So that's the first part. In order to do the second question, so you've got it into this matrix form, the state space form, you need to now get the characteristic equation. So in order to do that part, so say page 195 of Nelson, Flight Stability and Control, version 2, gives you following equation in order to work out the eigenvalues of a matrix. So it gets it into a characteristic equation form. Now if you apply this to the previous equation that we had, where our A matrix was xu negative g negative ZU on reference speed and 0, you end up with finding a determinant of, so because this is a 2 by 2 matrix, for a lambda I needs to be the identity matrix also as 2 by 2, so a 2 by 2 identity matrix multiplied by lambda would just give you lambda 0, 0 lambda minus XU negative G negative ZU on U0 and 0, which you end up with the following matrix. Now to find the determinant of a 2 by 2, it's fairly easy. So if you had a matrix which looked like A, B, C, D, the determinant of that would end up equaling AD minus BC. It's a little bit more complicated as you get to 3 by 3 and so on, but this one, fairly routine. So if you applied that, your characteristic equation would be, so 0 would equal lambda bracket lambda minus XU minus ZU on U0 G, and if you expand that out, you end up with a second order and that sort of equation. So now in order to get the eigenvalues, to see what sort of response you have, you first need to calculate out what XU and ZU are, so you can actually put numbers into your equation. But so this is the general form of the characteristic equation for a phugoid response. So the equations are given to you in the question. So you've got, to get the following stability derivatives, you apply the following. You've got all the values that you need. Now, even though they're in imperial form, as long as you keep them in the same format, you should be fine. So XU is negative 2 CD naught, Q, which is your dynamic pressure, S being your wing planform area, reference speed, mass, which is negative 2 times 0.05 times, so half rho v squared, rho being in imperial form, which is 2.377 times 10 to the negative 3, multiplied by 176 squared in this term, 184 feet for your wing planform area, divided by 176 multiplied by 85.4, and note that comes out to be about negative 0.045. Now your ZU, you can go through, calculate the exact same thing out. Only difference here is instead of CD naught, you've got the coefficient of lift, and I'm not going to go through the values, but it's 0.3696 for that value. Now if you plug those numbers back into your characteristic equation, which we had earlier up here, you end up with lambda squared. Now the negative XU, because you've got a negative value, becomes plus 0.045 lambda plus 0.3696 over 176 multiplied by gravity, which in feet is 32.2. So don't worry, if you get this sort of thing in the exam, you'll be given this value, so you won't have to derive it. Now if you calculate that out, it becomes So once you've got it into this form, so this is the characteristic equation, you can find the eigenvalues by finding the roots of this particular polynomial. So once you've got the roots, you can always plot it, say, on an S-plane, plot just to get an idea of what your response might be. So in this case, you've got the eigenvalues, which I'm not going to calculate out, but they are negative 0.0225 plus minus 0.259. So if you had a S-plane plot, you know that they would be sitting, so you've got complex conjugate pair sitting about, say, about here. It's probably not to scale, but now from that, because they're both on the left hand side of the plane, you know that you're going to get a stable response. And also what you can work out is you can work out well, you can work out your there's two ways to do it. Now you can either work out the damping ratio and the undamped natural frequency from this plot. So the way it works out is you can go omega, so this value here is equal to the damped natural frequency. This value here is equal to negative zeta omega n. So you can use those two to actually work it out, and you know that omega d is equal to omega n square root of minus zeta squared. So this is for, say, the people that did industrial control last year. But the other way to look at it is, so you can go through, you can work that out. The other way to look at it is you can compare this to the ideal characteristic equation, because, like I said, you know that they're on the left hand side of the plane. It's a complex conjugate pair, so it's going to be stable, and at the same time you know that because it's a complex conjugate pair and it's stable, it's going to end up being the damping ratio will be less than 1. So you can, in that special case, you can apply the ideal characteristic equation to it, which is 0 is equal to lambda squared plus 2 zeta omega n lambda plus omega n squared, and then you can directly compare against each other. So you've got and from that you should be able to work out what the damping ratio and natural frequency are. So what you do is you compare each of them. So for the lambda squared, you've got 1 against 1, which isn't going to give you anything. Then you've got 2 zeta omega n for the lambda to the power of 1 is equal to 0.045. And then, but you've got two variables in one equation. So from the third one, so lambda to the power of 0, which equals 1, so you can work it out from those indices. So for the last one, you know that omega n is going to equal square root of 0.076. So omega n is equal to 0.261. You can substitute that back into the previous equation and work out zeta, which will be 0.0867. And so you can work out a little bit more information there, but so that answers the part of calculating damping ratio and undamped natural frequency. But in order to comment on the aircraft response, if I flying qualities table for a level 1 aircraft, I know that zeta needs to be greater than 0.04 for a phugoid. So I've got 0.08, which is greater than 0.04, which indicates that for this aircraft it should have flying level 1 flying qualities. So once I have that information, I can work out a few other things as well. I can probably work out things like settling time if I wanted to, which is for 95% 3 on zeta omega n, which is about 130 seconds. But if I take a look at the rest of the information that I have here, I can see that this aircraft is flying relatively slow, doesn't have, you know, a large weight. The wing area isn't very large. It has very good flying qualities, so you can probably use that information to work out that, okay, this is probably a general aviation aircraft which is comfortable to fly and it's good for applications such as training.